Okay, good morning everyone. So today we will finish the last several slides for the ESD. So last week we have already discussed the basic related to ESD. So we have been talking about the silicon control rectifier and how will the ESD latch-up happening in our typical CMOS, which is mainly due to we have some parasitic coupling BJT. So once we have the ESD event, and once we trigger these parasitic BJT, then we will start to see the very high current happening. That's we call the latch-up event here. And then so we first to understand how we do the what happened due to the ESD issue, and then we understand how we actually qualify our ESD with a different testing model, with a human body model, charge device model, and we also talk about like the similar to the TLM, the TLP, the transmission line posing. And so the last part is mainly related to the how we try to prevent the ESD. So that's what we call the ESD protection strategy here. So the idea is very simple. Usually we consider this is inside our core IC, and especially the gate oxide is always the most weak part considered for the ESD event. So we already learned from the previous lectures that the gate oxide might have the issue, for example, the TDDB, also the BTI. So that also always suggests that our oxide can be very weak for the certain degradation. So what we try to have ESD protection is always we will insert some additional ESD component. For example, we can put some ESD component just before our gate oxide. And sometimes this is not enough, so we also will place the ESD component here for the IC packaging, even for the system level. So the protection network must be a device which will allow ESD current to pass through the ICs without causing any damage to either protection network itself or the remainder IC. So our idea is that once we have the ESD event, we have to make sure that the current can pass through this ESD protection. But of course, the most important is we need to make sure that this will not damage our ESD component, but also will not damage our the IC here. So we will shunt the current away from the sensitive circuit and prevent high voltage across the sensitive circuit. In here, the sensitive circuit here is mainly related to our core IC, which is our gate region. So if we talk about the ideal characteristic that we wish to have this protection device is, first we need to make sure this device has a good high current capability and low resistance. Also, we want to have a small footprint because that can reduce the size, and then we can avoid the cost. And also, we want to have a low parasitics. We want to have a low capacitance, low leach current. And one of the important is that it must be off during the normal operation. So that means once our core IC is turned on, we definitely hope all these ESD component is off and won't actually start to conduct the current. That will not avoid the typical function for our typical ICs here. And also, very important is it must be turned on very quickly during the ESD event, because as we already know, the ESD can be happen below the several nanoseconds, even down to the picosecond. That's possible. And several commonly used devices can be, the first one is a diode, because the diode has a characteristic, has a high current here and high current here. So that's exactly fit the part we wish to have for the high current capability. So this can have the high current capability and also the low resistance. So that's exactly fit. That's why we hope to use a diode as a very basic component for ESD. Although it's basic, but it's actually quite useful because the diode has a very simple structure. And also we have some additional, for example, the ground gate NMOS. So once we try to ground gate NMOS here, we can also have this snapback characteristic. So we want to leverage this part to start to have the current go through. So this one also provide us the high current. And of course that means a low resistance. So if we can place certain ground gate NMOS here, for example, if we place a ground gate NMOS here, and once this ESD is turning on before our oxide degradation, that means we can have a very high current shunt away from here. So the idea is very simple, just like in this way. And of course, we can consider to use a silicon control rectifier. And then the reason is that we also hope our ESD can operate in this region. Then we can make sure the current can be shunt away here. So the first one is a protection device. First one, the most common use is the diode. So diode is, as we already say, under the typical operation, we won't want our ESD device operate. So under the case without ESD event, the diode will be operate at this region. And that's good because that's a very low lead current and that won't influence our typical IC function. So this is a normal operation which doesn't have the ESD event. But once the ESD strike is happened, as already say, we hope to device, the diode can be operated in one side here or another side here, and that can give us a chance that the current can be quickly shunt away, just like in this case. So if once we have ESD pulses here, so the huge ESD pulse will cause this diode operate in the reverse of state, because this is a anode, this is a cathode. So that means the device actually will operate in this region. So at this moment, the device is start to operate in this region. Then we can make sure that the ESD event won't damage our device, because you already have the current shunt away, will not touch our IC and other functions. This is here, including the driver IC, controller, and so far here. And so ESD protection diodes are connected in the reverse direction, so they do not conduct when the voltage across the ESD protection is between the forward and then the reverse breakdown here. And here we have the two possibilities. One is using the unidirectional diode here. So in the case of unidirectional diode, the problem is that we don't have the symmetric waveform. We only have one is very easily to turn on. Another one, yes, the diode can be sustained high voltage here. But if we can use a bidirectional, we have the two diode connect with each other. That's we call it bidirectional. So we can make sure that our IV curve is very symmetric. So that's good for either positive ESD or either negative ESD, because we can always make sure that under the normal condition, the device, the ESD protection device, diode won't turn on. But if there's a negative huge ESD pulse, and then the diode can start to working, or the positive ESD event start happening, then diode can work. So with considering the bidirectional ESD that can be used to absorb the positive and negative ESD pulses. So this is example. So in reality, it's often to place a diode here and here. So the dual diode based ESD protection is a based non-ESD protection concept for the analog input-output circuit. So ESD dual diode typically constitute two diodes connected in parallel. Under normal conditions, the diodes are reverse biased, so they don't conduct the current. But as the voltage exceeds a certain threshold, for example, the breakdown voltage diode, the diode start to conducting, provide low impedance path for ESD current to flow. So that's we have already talked about. So once you have ESD event here, and this will start to turn on. Or once you have the ESD event here, you might start to also turn on this one as well. And sometimes, because of our gate oxide is very sensitive during the ESD stress, because our oxide is always very low. As we already mentioned, that the ESD voltage can be happen. If once the ESD event is happening, actually the voltage can be up to the several thousand volts. And usually our oxide only have the breakdown less than 50 volts, sometimes below 20. Even in the advanced CMOS, the oxide only has a breakdown below 10 volts here. So the gate oxide is always very sensitive during the ESD stress here. So therefore, we probably will consider that the several level protection here. For example, we can have the first one is a secondary ESD, and also we need to have the primary ESD here. So ESD stress applied at the input and VSS will first turn on local and secondary protection, which is this one. Secondary protection is here. This secondary protection clamp need to be lower than the failure voltage of the circuit. So this need to has a lower voltage compared to this one, because we want this one working ahead of our typical CMOS. So that's why we want to trigger this faster. So this one needs to have a lower failure voltage compared to this one. And also the higher voltage at the input pad will then trigger the primary protection, so which is this one. So that's a more system level consideration. Even the circuit level consideration where we will take into account for the two different protections. So another very simple protection device is that we call the MOS-based protection clamps here. But this is based on trying to leverage the parasitic bipolar operation. So we already know the typical MOSFET has a parasitic bipolar, but if we can ground the gate, if we grounded the gate almost, and actually this transistor will mainly operate like the BJT, like the parasitic BJT here. So therefore, we can start to consider turn on this NPN BJT. So we have this. This is our NPN BJT here. So the schematic for this one is that we will ground the gate here, and then we start to consider the operation for this BJT. And once, if we want to make sure this ground gate MOS can be turned on, the condition is that our substrate current times our substrate resistance need to be larger than this BJT turn on voltage here, which is this one. So the substrate current times R sub will be equal to the voltage here. This need to be larger than VB on. Then we can start to turn on this parasitic BJT. And therefore, we start to be able to operate in this region. And this can help us to make sure the current can be shunted away and without damage to our functional ICs. So this is also the typical, if we use the TLP methodology to test our ESD capability. So then we will also have very similar the snapback effect here. So the first snapback is the electrical effect, which is non-destructive. So that's the first snapback here. That's because of due to the parasitic BJT. But the problem is that if we continue to let the device keeping turn on in this region, then we might start to see the second snapback here. But second snapback might be the problem because this will cause the thermal failures. So that will cause the second breakdown here. So that's becomes the need to be something we have to worry. Like if once the ESD event is happening, but if our ESD cause a snapback and then the current is increasing up to a certain moment, we start to see the thermal degradations in our ground gate MOS. That will cause the second breakdown in our gate GG MOS. So this will cause a destructive event. So it's entirely to damage our ESD protection device. So the idea is similar. On the one side, we hope all these protection devices can start to operate before the ESD start to damage our core IC. But on the other hand, we don't want ESD event will damage this ESD protection device, because once it damages them, we lose the ESD protection capability. Okay, so the third one is very similar. So the typical characteristics that we already have mentioned before is mainly we try to leverage the latch up. And one of the advantages for silicon control rectifier that can be used for ESD protection is a silicon control rectifier has a lower holding voltage and lower resistance. And that gives us an advantage for the low power dissipation and high ESD threshold holes here. But the problem is that we need a very high trigger voltage, because we need to make sure that the breakdown between the N wheel and P sub here. And this also will be influenced by the substrate resistance, N wheel resistance spacing here. And also we usually need a trigger current. So we usually need a trigger current to start to operate in the latch up. So in here, in our lecture related to the ESD, we don't talk too much detail for each specific operation for the protection device, because you can feel that each one actually involves a huge knowledge that you need to have for the semiconductor device physics here. But but we provide some reference if you are interested in. For sure, you can look it up later. But in the purpose for this ESD lecture here is just give everyone a general understanding that what is ESD event, what will be ESD issue, what's the testing methodology, and in the end, what would be the possible solutions. Okay, so this is a final comparison with considering for the several different protection. So I think now I believe everyone get a little bit sense that when we talk about ESD protection, what we are carrying is always this part and this part, because we want to make sure our ESD protection device is be able to handle the high current and low resistance, and this part are the high current low resistance operation. So for example, if we only talk about this diode, then it's a forward bias and easily turn on, and it's very simple architecture. And also if we talk about this MOS, then we consider the snapback effect here. And also for the lateral silicon control rectifier, we consider the effect of snapback. But it's hard to turn on, so usually we need to have this secondary ESD. So these are the three we have been introduced. So although the ESD might be protected by our ESD device, but sometimes definitely ESD can cause damage no matter in our protection device or our core functional ICs here. So these are the several different types of the damage. The first one is the direct damage. So direct damages that will cause the half values, for example, physical destruction of the whole device, partial degradation of any part of the device, or other unrecoverable damages here. So it's kind of like the really damage our device, and that causes a certain very obvious degradation, and that's not possible being recovery. And the second one is indirect damage. Sometimes we call the soft errors. So this is actually, we don't see the obvious physical degradation that can be seen from the OM, from the TM, from all the material characterization. But these indirect damage that can cause a certain functionalities error. For example, if we look at the logic device, it can cause the logic state abnormal. So this can be only reset by the electrical or by other methods here. And the third one is the latent field values. So the device is weakened by the DSD event. So the ESD already creates a certain latent value. So the device is getting a little bit weak, but it will be fail after the later operations or by the later of the ESD, another ESD event. So this can be also caused by the ESD induced values. So here is a typical example that how the value signature that we can observe. So if we talk about the human body model or machine model, its typical device are energy related values like the contact spiking, thin film burnout. These are also possibly caused by the HBM or NM. But regarding for the CDM, that we might have the oxide damage, for example, dielectric breakdown, as well as some filaments due to this is because of the CDM has a high speed, high current discharge. This is something different compared to HBM and MN here. So here's an example. We have a silicide spiking, we have a gate oxide breakdown here. And one of the things, just a reminder that this is a very general case in a little bit old MOSFET. And for sure, the one that you are working on here, it's a very advanced transistor. In regarding for the advanced transistor, for sure, gate oxide is always the issue, because once you move to the advanced transistor, your oxide is getting thinner and thinner. Then gate oxide for sure is become the very serious for the ESD challenge. But regarding for the silicide spiking, that depends your process. So I would not say this is all these issues definitely can be happen in your case, but this is just remind you that if we consider the values under the HBM and MM, they probably have the very same symptom for their values, but the CDM might exceed a unique values compared to other modes. Now we look at what would be the challenge if we try to move on from the advanced node. So we have been talking about the advanced node can bring us lots of challenges in terms of reliability. In terms of BTI, we have seen because our gate oxide is getting thinner, we have to use a high K metal gate. And once you use a high K, then we suffer a huge defect in the high K material. And also for the FinFET, now we have not only for the planar BTI, but for the vertical channel, we also suffer the BTI, especially the vertical place has a different crystal orientation compared to planar, so that will cause the different trapping mechanism. And also for the TDB, it's also getting challenging if we move to the advanced, because our dielectric is thinner, so we have very huge direct tunneling, so our oxide is getting very weak, so we have to propose a high K metal gate, whatever, try to make sure that our device has a good TDB. And if we talk about the electron migration, we have been talking about in the advanced technology, what we are trying to scaling is not only the front end channel length, channel region, or front end transistor or oxide thickness. Actually, we try to scaling everything. That's including the area contact holes. That's including the interconnection width, line width. That's also including that we will try to passivate so many different materials as intermetal dielectric, try to stack. And even right now we have the TSV through VRs that will also cause we have a huge current divergence. And also once we move in for the advanced technology, then we also suffer the ESD issue is getting more and more issue. One of the issues is, for example, the oxide can be failure easier because of we getting more and more. We try to fabricate device with a very thin dielectric, so oxide has a very small breakdown voltage. Then we need to place a lot of the ESD protection, because the ESD voltage is not scaling, because the ESD is related to that how, for example, if we talk about the human body mode, it's mainly discharge between the human and to your device. So this voltage spiking won't decrease. It's always more than 1000 volt, even more than 10K volt. But the problem is that our scaling device, the breakdown voltage is getting smaller and smaller. This is because we try to reduce the pitch. You reduce the channel length, you reduce the LGD, that reduce the gate oxide. That's always cause a smaller breakdown voltage. And also the current handling capability also got the issues. Because if you try to make the very dense integrate IC, we already suffer the issue that the interconnection line has a huge current density. that also will cause if we try to reduce the interconnection line width, and then our driving current also reduce as well, and that will cause that reduce our current handling capability. So this is some of the example. This is you can see this is R side breakdown voltage fail. This is R side fail voltage. We can see once we moving down to the certain technology, and our R side breakdown voltage is getting smaller and smaller. But that's also caused, for example, this is TOP, this is ESD result here, and then so we can see the voltage also decrease, and also this is the current handling also decrease. And another one is our design window is shrinking with scaling. But the problem is that the real world ESD event doesn't shrinking. So for example, this is breakdown for our device here. So then, but this is a normal operation. So our breakdown is getting smaller here. So our ESD design window here is start to shrinking. So that can cause very complicated for our ESD protections. So the real world ESD events don't shrink as well. So this is one of the examples. This is also showing the same thing. Our gate R side breakdown is reduced, and therefore our ESD design window is also reduced as well. Okay, so here is some of the literature that you can try to look up by yourself, and then you can find some more interesting study that what would be the ESD happening here. So, and then probably we would, before we take a break, because now we have the presentation from you guys, just want to mention that I think so far we can stick to our original schedule. So my original schedule is that today we have one presentation, next week we have one presentation. So I think we can, next week we'll talk about something related to final exam, just pretty basic information. It's regards how we're going to run for the final exam, but in general it's as already said, it's an open book exam. You can bring whatever you want. But some of you have already followed my courses in the last semester. It's also in the final exam is open book, but the midterm exam is a closed book. But the result is an open book exam is always has a lower score compared to midterm exam. The one of the issue is that because you guys always feel like since this is open book, you can bring whatever you want. You don't read in detail, but that will cost you so much time wasting to finding the material. Even you can use Google, but I believe you just waste your time if you don't already have a basic understanding. But whatever you try to look at, we have if you try to look at the slide, some of you might print out all the slide or put it in the iPad, but probably the slide, if you try to print out, probably will be like this thick, and you will be completely overwhelmed. You don't know where to find the answer. And of course, the question is not that exactly. We have some basic question that coming from homework. So homework is the definite one. If you already very familiar with homework, no problem for you to pass this class. And by the way, the purpose for the graduate courses is not try to fail everyone. Just I know everyone is very busy on your own research. I think lots of you is already conducting the research right now. So the course is not like try to want to fail everyone. But we still need to have the fair way to evaluate the score for everyone, because otherwise it's difficult for me to put some score. So we still have the final exam. So we will talk about the final exam next week, and then so we have the protection. So I think we can stick to the same time on the December 16th for the final exam. So I think this is, so we won't have to find another time, because if we want to replace the time, then I need to find the time that fit everyone's schedule. Sometimes difficult, so I think we can still use December 16th as the timing for the final exam. Okay.